Okay, let's proceed with the second part for week 11. Okay, we have discussed the classification of PDE and we have some terminology. Okay, so what I will cover in this part is the method of separation of variables. Okay, this method is used to solve the PDE. Okay, and for this topic, we will just focus for the general solution of PDE. Okay. A solution of two-dimensional linear PDE in equation, the previous equation, okay, is a function of uxy of two independent variable. Okay, what is the equation? Is actually the auxx plus buxy plus cuyy plus dux plus and so on. It's equal to g. Okay, so okay, we have two independent variables here, which are x and y. So both independent variables, which are x and y, is actually denote the spatial variable. Okay, that is why this is 2D and two-dimensional. Okay, while for one-dimensional case, okay, where we have x and t as the independent variable, so x refer to spatial variable, okay, which is space, whereas t represent times. So I have explained to you previously on the previous part. Okay, all right. So the modeling of a physical problem is often done with PDE, which satisfies certain conditions on the boundary and at initial values. Okay, so these equations are called the boundary conditions and initial conditions. If you have the PDE, okay, together with the boundary conditions and also initial conditions, so we call this as the boundary value problem. Okay, so this is boundary value problem where you have the PDE together with the boundary conditions and also initial conditions. So actually for this week topic, we will only cover for PDE. Okay, we don't have the boundary conditions and also the initial conditions. So these two conditions we will continue on the next week topic. Okay, alright, so we only have one method, okay, one analytical method, which is method of separation of variables to solve the PDE, because this is actually the most effective method to solve several types of PDE. Okay, and Fourier series, okay, as presented in previous chapter, becomes a very important part when solving a PDE with the method of separation of variables, especially when we want to solve the boundary value problem, which means that if you have the complete boundary value problem where you have the PDE together with the boundary and also initial conditions, so in order to solve the boundary value problem, you need to implement or you need to apply the Fourier series solution, okay, in a part of the math steps. Okay, alright, so let's look at the method of separation of variables. Okay, so actually there are few steps, okay, but to solve the general PDE, you only need to apply two steps. Okay, so I will just explain this. Okay, there are several techniques for solving PDEs, analytical and numerically, so we will solve both. Okay, so separation of variables method is to solve the PDE analytically. Okay, alright, so this is actually what I have explained before. Okay, alright, so the main idea of the separation of variables method is we assume that the original function of two variables can be written as a product of two functions which each of the variable is only depends on their variables. Okay, we have the PDE, we have more than two independent variables in PDE, right? Okay, So this is the method of separation of variables, means that we will separate the independent variables. Okay, and from the separated equation, we have an equation that we can solve. Okay, we have two different equations that we can solve later. Okay, so that two equation is actually is ODE. So we will start with PDE. Okay, we separate the equation, and then from that separated equation, we will get two ODEs. Okay, two ordinary differential equation. So that two ordinary differential equation, we can solve it, and we can have two equations. Okay, and that two equation you need to combine later. Okay. Alright, so let's look at the first step. Okay, step one is to separate the variables. Okay, separating the variables. So a PDE is separable if it can be rearranged in such a way a function of x on the left hand side while a function of y on the right hand side of the equation. Okay, if you have the equation, the independent variables are x and t, means that you separate the variables. On the left hand side, maybe you have in x term, and on the right hand side, you will have in terms of t. Okay, so the solution of PDE, okay, will be in the form of uxy equal to x times y. Okay, still remember, so you have okay, you have for example, you have this kind of differential equation. Okay, so what you need to solve later, okay, using the separation of variable methods, later you will have the answer as uxy. Okay, so by using this method, okay, by using this method, we can have the final answer, which is uxy, and we will have as x times y, because from step 1 we can separate the variables, and from that separated variables you need to solve, okay, the ODE, and from that ODE you can have the solution of ODE where you will get x and also y, and then you need to combine it to get the solution of uxy. Okay, so x and y denote the functions of x and y alone. So x in terms of x, y in terms of y. Okay, and before we proceed with the general solution here, okay, we need to reduce the linear PDE into two variables of ODE. Okay, but we need to use, or we can apply this equation. We can write as del u del x equal to x prime u, because del u del x is we differentiate u partially with respect to x. Okay, so we can write x prime because we only differentiate with respect to x. Okay, but y will remain constant. Okay, because we first have this one. We have this one, u equal to x times y. Okay, so if you have ux, so it means that you can write as x prime y. Okay, if you have uy, means that x will becomes constant, only y is we put as the derivative. Okay, xy. Okay, if you have uxy, means that both, okay, you have second order and you need to differentiate for both variables. So you have x prime, y prime. Okay, what if you have uxx? So if you have uxx, means that we have double, okay, or second derivative of x. Okay, x double prime, y you just need to put as a constant. Okay, so this is the representation that you can have from the question. Okay, so normally, so in PDE, so it will start with the PDE, the partial differential equation. So that PDE you need to transform into this this type of notation. Okay, and then you can proceed with the step 1, which is you can separate the variables. Okay. Okay, so after you have constructed the x prime y, x double prime y, or y prime x, everything, so you need to divide by divide the ODE with the original function, which is xy. Okay, so when these steps you implement, so you will determine, you can have or you can show whether the PDE is separable or not. If it's separable, then you can proceed with the step 2. If not separable, so you cannot proceed with the next step. Okay, we cannot use the separation of variables method. Okay, so this is the steps. So let's look at the example. Okay, example 5.5a. Okay, state whether the PDE are separable or not. Okay, so for the first equation, okay, we have del u del x equal to del u del y, where we have u is equal to u in terms of xy. Okay, and we know that from this we have uxy equal to x times y. Okay, the final answer that you should have in order to solve this PDE is uxy, u in bracket xy, where you will have, since we want to use the separation of variables method, the answer will be x times y. Okay, right, so this is the equation. Okay, so this is the equation del u, this is the PDE. So this PDE we can write in terms of this one. Okay, if you still remember just now, if you have ux, we write as x prime y. Okay, same as actually ux is equal to del u del x. So we can write ux equal to x prime y, and uy, del u del y is equal to xy prime. Okay, alright, so this is the first step that you need to use. You need, in order to separate the variable, so first you need to rewrite the PDE in the form of prime double prime. Okay, so this is the equation that we have. So this equation you need to divide by xy. Okay, both sides, left hand side, right hand side, you divide by xy. So you will get what? X prime over x equal to y prime over y. Okay, I will show here. Okay, so you have x prime y is equal to xy prime. So if you divide by xy, so you'll have x prime y over xy equal to xy prime over xy. Okay, you cannot cancel out the x prime with x. Okay, but you can cancel out y and y on the left hand side, and on the right hand side you can cancel out the x. So that is why you get this kind of equation. So it will become x prime over x equal to y prime over y. Okay, and since you have on the right hand side is in terms of y, and on the left hand side is in terms of x, so therefore it means that you can separate the variables, okay, into two different two sides lah. Okay, so one is in terms of x and another side in terms of y. So the PDE is separable. Okay, so this how to show whether the PDE is separable or not. Okay, so you need to show that the variables can be separated. Okay, clear? So step 1 is to separate the variables. Okay, so this is example 1. Okay, let's look at example 2. Okay, the questions are still the same. Okay, you need to determine whether the PDE is separable or not. Okay, so let's try this. Okay, we have the same equation that you need to solve, which is uxy, because we have two variables there, x and y. So uxy equal to xy. Okay, and then from the equation, so you can rewrite the equation in terms of prime double prime. So we have the first term is uxx. Okay, differentiate u with respect to x twice. So that is why I have here x double prime y. Okay, and then second term, you have del squared u del y del x. So we can write as x prime y prime. Okay, and the third part or third term is we have the second derivatives with respect to y. So you can write as xy double prime. Okay, so all this equation you need to divide by xy, okay, to determine whether it's separable or not. Okay, first we construct or we rewrite in terms of prime double prime, and then you divide by xy. So when you divide by xy, okay, the first term, I will just write over here, okay, different colors. So x double prime y plus x prime y prime plus xy double prime equal to 0. So both sides I will divide by xy. Okay, so I will have like this. Okay, for the first and third term, I can simplify. Okay, y can be cancelled out. Third, I can cancel out the x terms. Okay, but in the second term, on the second term, I cannot simplify. I cannot cancel out the x and y. Okay, and therefore, since we cannot write x on the left hand side, y on the right hand side, or any combination, okay, so you have this one cannot be separated, the x and y. So therefore, we conclude that the equation is not separable. Okay. Alright, so this is the examples how to determine whether the PDE is separable or not. Okay, if it's separable, so you may proceed with the method of separation of variables. If not, for example, for B, so you just need to stop here. Okay, no need to proceed. Okay. Alright, so this exercise, you can try it later. Okay, you need to determine whether the PDE is separable or not. Okay, so we will move to step 2. Okay, in order to solve the PDE, the general PDE, we need to have two steps. Okay, step one just now is separating the variables. Okay, step 2 is to solve the separated equation. Okay, so from example 5.5a, okay, if you still remember just now, we have this kind of equation. After we separate the variables, we have this kind of equation where x prime over x equal to y prime over y. Okay, so actually we can equate it to a constant. Okay, so we equate it to k, a constant k, and therefore we will have two equations where one is x prime over x equal to k. Okay, this is equation 1, and equation 2 is, sorry, it's not x but y. So y prime over y equal to k. Okay, or you can write as x prime minus kx equal to 0 for equation 1, and for equation 2 you have y prime minus ky equal to 0. Okay, so actually these two equations, okay, you have these two equation is actually the ordinary differential equation. Okay, because the first equation we only have in terms of x, the second equation we only have in terms of y. Okay, it's just like what you have seen or learned in chapter 1 and chapter 2. Okay, we only have one independent variables. Okay, clear? Okay, so this is the equation. X prime minus kx equal to 0 and y prime minus ky equal to 0. So this equation is developed or is arise for the specific PDE just now. Okay, right. Okay, the equation just now, the PDE is del u del x equal to del u del y. We want to solve this. How to solve this is first step is you separate the variables, and then from that separated equation you have from this PDE you will get two ordinary differential equation. Okay, and in step 2 later you need to solve these two equations. Okay, alright, so we will proceed with the step 2. Okay, where step 2 is solving the separated equation. Okay, so since we have set the equation equal to k, so there are three possible cases that we need to consider, okay, in order to solve the equation. Okay, we will have three possible cases. Alright, so the first case is if we have k as a positive values. Okay, just now we have the equation y prime minus ky equal to 0, and another equation is x prime minus kx equal to 0. Okay, so we do not know what is the value of k, so k can be in three cases. Okay, one is k positive. So how we want to write k positive? So you can just write k equal to lambda squared. Okay, lambda represent any values. So if you have positive values, so k will be positive. If you have lambda as a negative value, so you also will have k as a positive value. Okay, so that's why we specify our case 1, we just set k equal to lambda square. Alright, so if we set k equal to lambda square, so we have this as the first equation, okay, where we have x prime minus kx equal to 0, and if we substitute k equal to lambda square, so you will have x prime minus lambda square x equal to 0. Okay, so we need to find the solution for x and also this y. Okay, for both equation 1 and equation 2, when we substitute k equal to lambda squared, so we will have two equations again, and this equation you need to solve. Okay, how to solve that? You can apply the formula or the method in chapter 1, okay, because this is first order. So chapter 1, which is it's a linear equation, so you can apply that, or you can use from chapter 2. Okay, if you still remember, okay, table 2.1, so you have three possible values. Okay, if it's real and distinct, okay, real but repeated, and also complex conjugate. So you have three different cases, right? The roots. Okay, so it's actually depends on the root. Okay, so for first order differential equation, so how are we going to find the roots? So actually it's the same. So if you write in terms of m, so you will get m minus lambda square equal to 0, and therefore our root is only one, which is lambda square. Okay, so this is just a substitution. If you have y double prime, so you change it to m square. You have y prime, you change it to m. and if just constant, you just put as the constant there. Okay, so this kind of equation, so x prime minus lambda squared x, you can write in terms of characteristic equation, which is m minus lambda square. So m minus lambda square equal to 0, so you will have the root is equal to lambda square. You only have one roots because this is linear. Okay, alright. So and since our root can will not be a complex conjugate, okay, it only have a positive not positive real numbers. So if you refer to table 2.1, you have two solution for real numbers, which is one is real and distinct, one is real but repeated. Okay, where for real and distinct, the first one, you will have the general solution is a exponent m1x plus b exponent m2x. Okay, and for second condition here, you will have the answer, or the general solution is a exponent mx plus bx exponent mx, because we have the same root. Okay, but since our roots only one, so you don't consider the second part. Okay, so you only consider the first term here. So these are the same. So the general solution for first order differential equation here is actually equal to a exponent mx, where m just now we get as lambda square. Okay, is it okay? Alright, so the first equation is in terms of x. So therefore, the general solution also is in terms of x. So x in terms of x is equal to c1 exponent lambda squared x. So it's just the same, the different only this a. I used c. Okay, c1. Why? Actually, you can use any constant because we will have more we have two equations, so you cannot put a and a, you cannot use the same constant. Okay, so I just put c, and then for y, okay, for this equation, what color this one? So for this equation, so for this ordinary differential equation, you will get this as the solution. So you will get y in terms of y equal to c2 exponent lambda squared y. Okay, is it okay? I hope you understand. If you didn't understand, so you can ask me later. Okay, you can text me. Alright, so this is x and y. Okay, so next is to find the general solution, okay, where you need to combine x and y. So you need to multiply this. So you have x equation and you have y equation. So you need to multiply that. And since we have c1 and c2 are constant, so constant times constant will get another constant. So I can put it as a1. Okay, and you can use the property of exponential. Exponent a times exponent b is equal to exponent a plus b. So that is why you will get this as your answer. Okay, and this is the solution. Okay, this is one of the general solution for the PDE. Okay, why I said one of the solution? Because this is for case 1 only. Okay, still remember? We start with these two equation, kan? So these two equation, we have three possibilities for k. Okay, so we only solve for the first case, which is case k equal to positive, or we set k equal to lambda squared, and the answer or the solution is given by this equation, this function. Okay, so this is the first solution. Okay, right? So next is case 2. Case 2 is we set k as 0, k equal to 0. So we will have, at first, just now, the first equation is x prime minus kx equal to 0. Okay, the same equation. So when we substitute k equal to 0, so you only have x prime equal to 0 and also y prime equal to 0. And if you find the roots, okay, you can change this equal to m equal to 0. So the root is 0. Alright, so if you have root as 0, so the solution is y equal to a exponent mx. So if m equal to 0, so you will have a exponent 0x, or we can write as a only. Okay, because exponent 0 is equal to 1. Okay, so that is why I didn't put a, but I put just a constant C3 for general solution of x. Okay, same as y. Okay, y, when we solve this, so the same root, which is 0. So if you have m equal to 0, so the general solution for y is equal to constant. So I put it as C4. Okay, and therefore, okay, you need to combine u equal to x times y. So you'll have C3 times C4, okay, constant times constant, where you can get another constant, which I put as A2. Okay, so for case 2, which is k equal to 0, is quite simpler than case 1, because the root is 0. Okay, so okay, next is if k is negative. Okay, so if k is negative, we set k equal to negative lambda square. Okay, so when you set k equal to negative lambda square from the first equation, which is x prime minus kx equal to 0, so you will get x prime minus negative lambda square x equal to 0. Okay, negative and negative becomes positive. So you will get this equation. Okay, so x prime plus lambda squared x equal to 0. And for second equation, you will have the same but different variable. So we have y prime plus lambda squared y equal to 0. Okay, so again here, okay, if you find the root, so you will get m equal to negative lambda square. So only one root, so this will consider the real numbers. So just the same, okay, where you will have y equal to a exponent mx. Since our m is equal to negative lambda square, so our general solution for x is c5 exponent negative lambda squared x. And for y, it's c6 exponent negative lambda squared y. So make sure you put the same variable, x, y, y. Okay, and finally, you can have the general solution, which is uxy equal to x times y. So you just multiply the x that you have obtained with y that you also have obtained before. Okay, and using the properties of exponential, so you can get these answers. Okay, where a3 is equal to c5 times c6.